Sure. Yeah, it is 9:30 now, so we'll start. So very good morning to all the participants who have joined for this workshop. Welcome to day 3 of this exam 2021 workshop. And today, today we'll be hearing from Dr. Sugandha Maheshwari, who is Inspire faculty at ISR Mohali. She has done its MSc Honors and PhD from Punjab University, Chandigarh. She has qualified her CSIR UGC JRF plus NET in 2010 with All India rank of 8 in the first attempt itself. And she is also CSIR Shama Prasad Mukherjee Fellowship Awardee in 2011 among the total of 4 awardees. So that is very interesting, very honor of this award of this Shama Prasad Mukherjee. She is also qualified this GATE 2011 with All India rank of 10. She has qualified JAM, Joint Admission Test for MSc from IITs in 2009 with All India rank of 47. She's also got this MSc and BSc NBHM scholarship in 2006 as well as 2009 to 11 batch both for BSc as well as MSc. She's INSER faculty awardee in 2017. She has got this BSc National Postdoctoral Fellowship by SCRB in 2016 as well. She is a member of INEAS and also core committee member of INEAS since last year. And she is also formerly coordinator of INEAS Chandigarh chapter. She has received several grants for her international research visits. She has done several innovative talks and presentations at various national and international conferences. Published several papers and book chapters in reputed journals of algebra. And she's also author of Software Package, GAP Vederga. She's reviewer of American Mathematical Society. And right now she is 5 years into teaching and research. And she is very active in outreach activities. And this particular workshop, Exam 2021, was actually headed by Dr. Sugandha Maheshwari. And she has taken along with her all the maths colleagues for this workshop. So she will be talking today on abstract algebra for this today day 3 of this workshop. So with this short introduction, I welcome Dr. Sugandha to deliver a lecture. Yeah, over to you, Sugandha.
Thank you, Vivek, for your kind introduction. So before I proceed further, I will share my screen. Let me know when the screen is
started sharing.
Okay.
Yeah, it is done. Yeah, let's start.
Good. So good morning, everyone. So this is day 3 of the workshop. And as you know by now, and as Dr. Vivek also mentioned, I'll be taking your 2 sessions on abstract algebra. So in the first half, we will be talking about group theory, some topic from there. And in the second one, we'll be talking of some parts from ring theory and field theory, right? So in the group theory, I'd like to talk about order of groups, their elements. So very basic notion, once you have had a course in group theory, you know what is order of a group and what is meant by order of an element. So this is a very basic concept, and I just like to go about around the results around them and how these can be used to solve certain important questions, certain questions that you get in these exams, right? And just before I start, owing to time restrictions, let me tell you, I'll not be going into the details of the proof. So you will have to excuse me for that. And also I have this habit of putting up several questions for you to think the exercises as homework. So to make this learning effective, to get grip of everything that I tell you, please go through them, please work them out, use pen and paper, and just don't be passive audience. This is the only thing that I would like to say. Okay, so without wasting any time, let's just quickly recall what is order of group. So order of group, as you know, it is simply the number of elements that are present in that group, right? It's cardinality, or roughly speaking, it's size. What is the size of the group is given by the order of, is what we call as order of group, and mod G is generally the notation that we use for it. It can be finite, it can be infinite, right? If I ask you the converse question, I mean, if you have a group, if you have a given group, of course, you can tell me what is its order, right? You can tell what is its size. But conversely, if I ask you, if I give you order of the group, and then I ask you how many non-isomorphic groups of that order exist, right? How many groups or what kind of groups can you have with that order in, then what will be your answer, right? So in general, let me tell you that this is a non-trivial question. I mean, this is not very directly answerable given arbitrary n, right? A lot of work has been done in this direction, which takes huge effort to understand, and also a lot of work is going on in this direction. But we can at least talk of some particular values of n, right? So let's just take some very simple cases briefly. For example, if you have this n equals p, okay? You have a prime number p and you are looking for groups of order prime, right? So at this point, maybe you know the answer and you just feel free to write your answers or your views in comment box. I do have a screen where I see YouTube live. So maybe I'll be looking at some of the comments time and again, right? Okay, so if you have n equals p, in that case, probably you know the answer, right? You are going to get cyclic groups of order p only. So just look at this. What is the result which gives you the answer, right? You are aware of Cauchy's theorem, generally taught in first course of group theory, but let me just recall it for you. So if you have a prime P which divides the order of group, then G does have an element of order P. There is necessarily an element of order P. So if your group is of order P and there is an element of order P, it has to be a cyclic group, right? There is no other choice. So we do have a clear answer for this, that this group is going to be isomorphic to a cyclic group of order P, right? Here, I would like to just point out a few things about cyclic groups of order P. They are simple groups. They do not have, what are simple groups? So, okay, what are simple groups? The groups which do not have any proper subgroups. So by that, I mean, other than the trivial subgroup and the group itself, those are always going to be subgroups of given any group. Apart from that, if you don't have any group, any subgroup of a group, then it is called a simple group, right? So if I ask you more examples of simple groups, can you give that? So let's just take some questions in order, right? So if I ask you question 1, give me an example of abelian simple group. And let's just restrict ourselves to finite. Ideally other than CP. Then what is your answer? Okay, so can you find out some abelian simple groups different from cyclic groups of order P? Second question could be, if I just delete this abelian. So I'm asking you, can you give me an example of a simple group different from cyclic groups, right? Then if you're able to answer this, of course, there will always be a greed of putting a next question for me. So may I ask you, can you tell all finite simple groups? Right? I do not expect you to give complete answer. It's not a trivial problem. Again, we do have a solution for this, but this is non-trivial. In fact, You can do a project on this, classification of finite simple groups. You can do a project on this. So what is my idea of putting up some questions here is I just want to highlight how and what you should be thinking while preparing a topic or a concept. There should always be a habit of having this curiosity. Okay, does this always hold true? Where does this hold true or where not? Can you find one example, right? Existence, can you look for all examples? So this gives you a better grip and better understanding of a concept. So just go about these questions, enjoy finding out some very nice facts about simple groups. And of course, you'll realize that this name is quite deceptive. Simple groups are not at all simple. Okay, so with that, I'll move on to what we were doing. N equals P squared. So suppose if you have a group whose order is P square. So you must be aware of this result, but I'll just recall groups of order P square are abelian, right? If you haven't seen this theorem, seen this result, you must work out the proof of it. It's an elementary proof, understandable, but you should be aware. And if a group is abelian, and you also know its order, then which theorem comes to your rescue? Which theorem gives you all possibilities? That is fundamental theorem of abelian groups. Okay, you might have seen this, and those who have understood the proof of it or seen it anytime must have realized that proof is little involving, right? But the result is something that you should always be ready to apply. Let me tell you how to apply this result. You will be using this time and again in our lecture today. I'll be using this very often. But for this group, let me tell you particularly, you don't even need to use fundamental theorem of abelian groups. You can go by elementary methods also to prove that there are only two groups of order P square, which are CP square and CP cross CP. Maybe I'll write here for better visibility. CP square, cyclic group of order P square, and direct product of two copies of CP, right? So, I'm sorry. Yeah, so with that, I'll just proceed a little further and then I'll come back to this fundamental theorem of abelian groups as well. All right, so let's look at next case. What is next possibility that we can answer? So that is about when the group has order n equals 2p. So we are moving from one prime to product of primes, but we are taking very simple cases. So in this case, suppose if your group is, it can be either abelian or it can be non-abelian, right? So if it is abelian and if we apply fundamental theorem of abelian groups, what is your answer going to be? So you have this order as 2p, right? So the only possibilities are C2 cross CP, and because P is an odd prime, 2 and P are relatively prime, this is isomorphic to cyclic group of order 2p. So there is only one possibility of abelian group of order 2p, and if it is non-abelian, then your answer turns out to be dihedral group of order 2p. I'm not going into the detail of proof, but again, I would say this is accessible and understandable for you. So dihedral groups of order 2n. Just few things that I would like to highlight about this dihedral group. When you started the course on symmetry or course on group theory, you must have seen the rotation, the group formed by rotation and reflections of a square, symmetries of a square, which gave you this group D4 or D8. That depends on what notation you are using. Sometimes it is called D4. So this is group of order, I'm sorry. This is group of order 8, right? Sometimes it is denoted by Dn, sometimes it is denoted by 2n, but then it's mentioned which order you are taking. Right, so in case you take an n, what's happening? In case you take a group of, in case you take symmetries of n-gon, then it gives you the group of order 2n, dihedral group on n gone is a group of order 2n, and with n equals to p, I am saying that that will be the only non-abelian group of order 2p, right? So as of now, you may just remember that there is one abelian group of order 2p, which is cyclic, and there is one non-abelian group of order 2p, which is dihedral group, right? And if you move on to the next case, n equals pq, right? This has two possibilities. Again, let's look for abelian first. So abelian, this is going to be Cp cross Cq, which is isomorphic to CPQ because P and Q are distinct primes. In fact, we can always assume that one is lesser than the other, right? So in this case, you have two possibilities. Either P divides Q minus 1 or P does not divide Q minus 1, right? In case P does not divide Q minus 1, this will simply be, there will be no non-abelian group. This will simply be CPQ only. Okay, and in case it divides Q minus 1, then you are also going to get a non-abelian group, which will be metacyclic group. There's a unique metacyclic group of order PQ. At this stage, you might not know what is metacyclic, right? And even you can just forget this term. Just remember that there is one possibility of non-abelian group in case you have this order. Right? So what do we have? We have CPQ and CPQ, comma, this, how do I denote metacyclic group of order P? So I'll just write non-abelian of order, unique non-abelian of order PQ, right? So this is when P does not divide Q minus 1. This is when P divides Q minus 1. All right. And so, okay, let's proceed further. So if I ask you, if I give you this homework where you have to write all possible groups of order at most 15, all non-isomorphic groups of order 15. So let's see what all do you need to do for this. You have this, I'll just quickly write down these numbers. Let's see what all you need to do and what is left so that it doesn't seem I've given you a lot of work to do, right? So this is trivial group, you know. This is, so let's first cancel all the primes. So because CP, you know how to handle. So this is gone and that's it. So all primes, you know, there are only precisely one cyclic group of order each of these primes. I'm sorry, this also needs to be cancelled. So this is P square, right? This is in the category 2P. This is P cube. This we have not yet talked about. This is P square and we know how to handle this. This is 2P, this is P. This is 2 square times 3. So this is P square times Q, right? This is something we have not done. This is P. This is again in category 2P and this is PQ, where P does not divide Q minus 1. So it's only the case 8 and 12, which I have not talked about. And if you work out these examples, also the other cases where I've left the proofs and you go through all the details that you're using, so that will brush up a lot of concepts from group theory, right? Like fundamental theorem of abelian groups, Cauchy's equation, Sillow's theorem, class equations. And if you go up to say order 20, having got grip of these, suppose you go up to order 20, then you are going to be involved with the concepts of direct products and semi-direct products also, right? So semi-direct product will come into picture if you go up to order 20, and that will give you a very good grip of group homomorphisms, automorphisms, and everything, right? A very basic exercise, but I suggest every student must do this once you have had a course in group theory to recall all that you understand about groups and their structure, right? Okay, so with that, maybe I'll proceed further. Okay, regarding 8 and 12, maybe at this point, it's good time to see how to apply fundamental theorem of abelian groups for those who have not used it much or who are not very much familiar. So look at this, n equals 8. So this I can write as 2 to the power 3, right? So just write prime factorization. Look, I'm just telling you how to apply this to find all non-isomorphic groups of abelian groups. So you have this power 3. So you have to look at power of every prime which is involved and look at the partitions of 3. The number of ways you can write this as 3, 2 plus 1 as sum of natural numbers, right? 1 plus 1. These are the only possibilities. Okay, so in this case, if you have to write down all cyclic groups, what will those be? So from the first one, you get the same prime and this power 3. From the next one, you will get C2 square, direct product with C2, understandable? And from this, you're going to get C2 times C2 times C2. Okay, so similarly, so there are 3 abelian groups of order 8, and if you work out, you will be able to see there are 2 non-abelian groups of order Q8, or of order 8, right? D8 and Q8. By D8, I mean the dihedral group of order 8, right? It is again symmetries of square. And if you look at this 2 square times 3 again, so can you now tell me what will all abelian groups be? So from this, the partitions are, the possible partitions give you C2 square and C2 cross C2. For this, you have only choice as C3. So you have 2 non-abelian groups of order 12, right? And for non-abelian groups, I'll leave this question open for you to think. So let's come on to some questions quickly. And this is question from June 2014. This is a single option question. So now you're in position to answer this. So can I just see some comments answering me this question? There's some time lag, so maybe okay, so this is 2p, right? 2 times 61. 61 is a prime number. And so how many non-isomorphic groups of order 122 you can have? The answer is very much clear to you. Yeah, now it appears on YouTube. Right, see, I see some answers too. So it is 2p. So clearly you're going to have one abelian and one non-abelian group, which is going to be, so this is D2p and C2p that you will get. Right, so some of you have given correct answer and I'm happy about that. All right, so let me proceed to the next question, which asks you, for a group of order 77, what are the possibilities of center of G, what it can be? So let's first understand what is this group, if we can get a hold of this. So what is 77 equal to? This was question asked in 2011. Again, single option. Of course, the answer cannot be 2 options for such a question. So this is 7 times 11 that you have. So you are in the case when P does not divide Q minus 1, right? 7 does not divide 10 here. So this is going to be a cyclic group of order 77. There is no other possibility. And if group is abelian, it is same as its center, right? So you have your answer as D. And I see answer from Amardeep as D here already. So that's good. Keeping in mind that there is some time lag also. So it's good. Okay, up to isomorphism, how many groups of, abelian groups of order 108 are there? So you just have to apply your fundamental theorem of abelian groups. So what do? First is you look at the prime factorization of this. So this is 2 square times 3 cube, right? 27, 4, right, 5400. All right, so this is a group with this prime factorization. So what are the possibilities of partition of 2? This is 2 or 1 plus 1. Here you have 3 partitions, which are 3, 2 plus 1. You have 1 plus 1 plus 1. So you get 2 groups from here, 2 cyclic, 2 possibilities of groups from here and 3 from here. And so your number is going to be 6. Is that clear? Does that need, okay. Okay, in case there is some doubt, you'll be writing a little later. So you understand the kind of groups which will come into picture. So this will be C2 square times C3 cube, or then next will be C2 square C3 square times C3. So you can keep changing the options here, and you're going to have by counting principles, 2 times 3, this is 6. And there's answer by Kritika also, Sheetal also, and most of you have got it correct. So I'm happy about this. Okay, so maybe these are very easy questions to begin with, but these are all the questions from your entrance exams. So even if they're easy, they're going to fetch you marks, and that's not bad. All right. So my next question is, if G is a non-abelian group, then what possibly its order can be, right? So you have already seen you have restriction on G being abelian or non-abelian depending upon its order. So look at this 25. What is this? This is P square, and groups of order P square are abelian. So you do not have this option. What is this kind? This is 5 times 11. So prime factorization is something very important, and I'm just writing that. And this is 5 times 7. Okay. So again, in this case, you are in the case where this does not divide this. So this is ruled out because there's only cyclic group of this order. And the remaining 2, here you have an abelian as well as non-abelian group of order 55, right? I'm sorry, this is not to be a metacyclic group of order 55. And so there is indeed, and also for P cube, there are, in fact, there are 10 non-isomorphic groups of order P cube. This is the reason I've not picked it up for here. If P is an odd prime, you have 10 non-isomorphic groups of order P cube. So these two, both of these two are correct options. This was a multiple correct options question, and you know that they always fetch you more marks than the single option, right? Just the order of group, you have little understanding and you're able to attempt this question. This was also asked in one of the exams, 2014 December it was. And so I see some single answers being received, but there is some mixed response. So not everybody gets correct answer, but Kritika has got it right. Okay, let's move further. I hope I've not missed any question. Yeah. Okay, so let's move to. Okay, so next I'll be moving on to order of element. You have seen about order of group. Now it's time to talk of group of element of the order, right? Order of element of group. Okay, so you understand what is it? It's the smallest power such that many times you multiply and you reach at the identity of the group, right? So you very well understand what is meaning of order of element. And if not, you cannot survive with this group theory part. And what are the facts that you know about order of group elements? One thing is that this order has to divide order of group, right? This always is true. And what is the reason to that? Can anybody tell me? So, okay, before I proceed further, there's a question of some student asking what is total number of groups of order P cube? Okay, P cube, you know the answer for abelian case, and for non-abelian, if P is even prime, that is if P equals 2, then this is, you have 9 non-isomorphic groups of order, I'm sorry, it was for P raised to power 4 that I said. For P cube, I think I misstated earlier. So let me just write it down here. For P3, P to the power 3, you have 2 non-isomorphic groups of order P cube, whether P is an odd prime or even. For P to the 4, there are, so partitions of 4 are 5 in number, so 5 abelian groups. And then you have 10 non-abelian groups of order P to the power 4 in case P is odd, and 9 non-isomorphic groups of order 16 if P is 2, right? That's the answer. So thanks for asking that question. I gave a wrong statement earlier. All right. So by Lagrange's theorem is rightly given by Shivam that by Lagrange's theorem, you do have this thing that the order of element divides the order of group G. Okay, what is Lagrange's theorem? Again, it is written over here. It states that if you have a subgroup of a group, its order will divide the order of group, right? And because if you have an element of order, say n, then you can always look at this subgroup generated by that element. That will be a subgroup of G, and that its order has to divide the order of group G. That's how you have that order of element must divide the order of group, right? Well answered. Okay, so and the reason was also given by Chinmay, I can see. Okay,
it's 10 o'clock.
Sorry. Okay, so then you must realize that converse of Lagrange's theorem is not true, right? I'll also give you one example that every book or every teacher will give you, that this is the simplest example where you see it fails. Alternating group on 4 elements. This does not have a subgroup of order 6. So clearly Lagrange's theorem is not true in general. You cannot apply, you cannot say that for every divisor D of n, you are going to find a subgroup of order n. That's not true, right? But as usual, the questions should be there, the curiosity should be there. Are there some groups for which Lagrange's theorem is true? One class of groups that I think you know for sure is abelian groups, right? For abelian groups, everybody knows that for every divisor, you will be able to find a subgroup of that order. And you must have seen the proof of that as well. But are there other groups that you know where it will hold true? For P groups also, you know, maybe not directly, but you know the answer. Can you tell me why the converse of Lagrange's theorem is true for P groups? It's time lag, which is creating little trouble, but I expect some answers from you. Okay, maybe I'll not waste much time. So it's Syllo's theorem which come to your rescue, right? Directly from Syllo's theorem, you get that for P groups, Lagrange's theorem's converse has to be true. One can verify for the groups of order PQ also. In fact, one should look into groups of square free order, but anyhow, I'll not go into the details. For S4 also, I mentioned this particularly because it fails for A4, but it is true for S4. S4 is a group of order 24, right? Symmetries on group of symmetry on 4 elements. So this does have elements for all orders, and this you can directly do by calculation. So you have 24 as order and you know all the divisors. No, I missed 6. And you will be able to write a subgroup of order each of these orders one by one if you start writing, right? That won't be a problem. Then there is another question in this direction I have. So please just check out for these groups. These are within your reach. That's why I have listed them here. Otherwise, you have big classes coming into picture. You can even take it as a topic of one of your projects, a simple summer project. The groups for which converse of Lagrange's theorem is true, right? Super solvable groups, for example, come in this category. And also we know that the groups where it is true have to be solvable and so on, right? There are various things that you can study about around these concepts, but these are very well within your range. Okay, so now let me ask you another concept. So going through these, you will have to revise Sylow theorems and class equations, so everything will be covered up there. So given a group G of order n, now my next question is, what about existence of elements of order D? And suppose they exist, right? So the first one was about subgroups. Now it is about the element, right? Already by Cauchy's theorem, you know that if P divides order of G, there is an element of order P. Now my question is, if D is any divisor, then what can you say about existence of elements of that order? And in case you can find, how many of them are there? Right? So how many groups of order D are there? So for this, you might recall or maybe just check this out, that if D divides N, then number of elements of order D in cyclic group of order N equals phi-d. Phi is Euler's phi function. If you don't know what is it, please find it out. You cannot just leave it, right? Euler's phi function. You should be very well familiar with this. And why is this? So it simply uses the concept of the order of element. What should be the order of an element A to the R? If you know the order of A, can you find out the order of A to the R and simple GCD concept? So very elementary result. And this is what I'm leaving as exercise for you to find out these facts. So here are some classes of groups that I think you should go into detail for studying. You should be aware of these. Abelian groups, of course, you have to begin with abelian groups for whatever things that you study. Then look for dihedral groups. What are they? You just need to understand these groups once and they will stay with you forever, right? Dihedral groups, what are its elements when n is odd, when n is even, I mean n-gon I'm talking about. Then how are the situations different? What are their central elements? What are the orders of the elements that you have? What are the cyclic subgroups they have and everything. So just spend a day, go about studying what are dihedral groups, what are symmetric groups and alternating groups, what are their elements, and all these questions you should ask yourself, and whatever you don't know, just go back to your books and study them. For example, in symmetric groups, a lot of questions around possible order of elements are asked, right? And if you have a cycle of length n, then that has order n. Every element can be written as product of disjoint cycles. And then you know about the order of product of cycles also. That happens to be LCM of order of each of the cycle and so on. There are various facts associated which are easy, trivial, but then you need to have a good grip over them. And similarly for alternating groups also, you should be familiar with these standard basic groups. Another class of groups which you should be familiar with are general linear groups and special linear groups, right? So you understand the group of matrices over some field, right? This can be generalized to ring also, but let me just restrict myself to MNK for the time being. So if you look at matrices which have non-zero determinant, right, that forms a group under multiplication, and to that we call as general linear group. Similarly, if you look at all those matrices where determinant is plus minus 1, then you call them special linear groups. So you should be aware of the number of elements in these groups, or how to, what is the structure of these groups and so on, right? What are the elements which will commute? These are not abelian groups, right? These are non-abelian groups. And also the properties of direct products and semi-direct products. What are, what is the difference between direct product and semi-direct product firstly, and the group action that comes into picture into semi-products and everything, right? So as I told you earlier also, I'm just telling you how to study, how to prepare. All right. So with that, I'll move on to my next part, which is, I think I missed a slide, maybe. Okay, so if you have a group G of order 36 and there is a subgroup of it which is of order 4, then what can you say about this? Again, this was a question asked in multiple correct options. So you have to screen out all options. You cannot go by method of elimination. So the very first thing that should come to your mind is, it is a subgroup of order. You want to talk about this, right? This is a subgroup of order 2 square. This is a subgroup of order p square, right? And groups of order p square are abelian, we have seen. So at least this D option is correct for sure. But then you cannot stop here, because this is, sorry, because this is multiple correct options you can have. So let's go over one by one. You have this group of order 36. Can you have abelian group of order 36? In fact, that's a bad question, because for any order n, there is always an abelian group of order n, which is Cn. Of course, there will be abelian groups of order n. Kitne honge, that will be answered by fundamental theorem of algebra, but then you always have one at least. So are there non-abelian? So if suppose G is an abelian group of order 36, its center will be equal to the group itself So that will have order 36. So of course, this is not necessarily true, right? If you have group of order 4, that need not be the center of group because G can be abelian. Okay, so let's talk of the option A and option C. Look at option A. Now you have this group of order 36. Should a subgroup H of order 4 always be in the center? One class of non-abelian groups that you know by now is of where you can have order 36 is that of dihedral group, right? Look at 18 GOM or dihedral group of order 36, right? So in that, if you know about the center, as I left you in the previous slide also that you should be knowing about center and everything. So this has 2 elements in the center. In fact, let me tell you, D2N, this has center as trivial if N is odd, and this is isomorphic to C2 if N is even, right? So this is generated by rotation of 180 degree, which is missing in case N is odd. In a pentagon, you cannot have 180 degree rotation. And if N is even, then it is isomorphic to C2. So there are only 2 elements in the center. So this subgroup H will not enter into the center. So this is not always true, right? One counter example makes the statement false. And regarding H is normal in G or not, owing to the restrictions of time and everything, I cannot right now explain you semi-direct product. I see in one of the comments also this is asked what are semi-direct products. So here I leave you that there is a semi-direct product, there is a group of order 36 which is semi-direct product of C9 and C4 where this is a normal subgroup of that group. And this is not normal. Okay, so to understand this thing, you need to understand some concepts of group automorphism and action. Sorry, excuse me for the timing. Just I cannot go into the details right now, but this is something important. You should look into it. Okay, so I'll move on to the next slide now, where I can probably take another question. Right, this is the one that we'll talk about now. So Sn is group of permutations on n symbols, symmetric group, as you know. So you're asked this group S3, this was asked in 2013, and though it was in the category of multiple correct options, so you fetch more marks for answering this, but you know that up to isomorphism, all these 4 groups are different. So there has to be only one single answer, right? Okay, look at the question is, what is S3 direct sum with C2? C2 is also denoted by, notation, whatever is convenient to you, but you should be familiar with all depending upon what is used in the paper, you will also use the same. So you have these 4 options and you have to tell what is this direct product isomorphic to. So the very first thing is, what is its order? The order of this group is 6 times 2s3 is of order 6. And so this is 12, but then all 4 options are of order 12. So you cannot eliminate any of them. But there is another thing that you can observe. S3 is non-abelian. In fact, it is the smallest non-abelian group known to you. So S3 is non-abelian. So options A and B can definitely not be your answer, right? Because they are both abelian. That's one thing. Regarding A4 and D6, now you have to make a choice. So what I do is, about A4, I know something that it does not have a subgroup of order 6. Subgroup of order 6, right? But if you look at this group, you have a subgroup of order 3 here, and C3 direct sum with C2, this will be a subgroup of order 6. So of course, this is not an option, and then you get this, right? My question at this stage to you, again, I'm very, greedy in putting up questions and asking you so many exercises. So you have S3 cross C2 is isomorphic to D3 or D6 as you call it, group of order 6. Okay. This is not, I'm sorry. Yeah, this is not true in general. I mean, this Sn cross C2, of course, this is not isomorphic to some D2M always, right? So just try to look into it. Is there some general pattern? Do you have S4 cross C2 isomorphic to a dihedral group of whatever correct value of N should be or something? Right? I mean, I'm just putting up some questions. Like these are the questions which should come to your mind, that this is happening in one case. Does this happen in general? Does this happen for some other cases? Right? Okay, so with that, I'll just move on to next question probably. Okay, so now I'm asking you, if G is in fact not me, this was asked in 2016 in the NET exam itself. So again, a question revolving around order of group and subgroup and elements. What does it say? G is a finite abelian group. They're nice people, not asking you any difficult group. G is finite abelian group of order n. Then what can you say about what are the correct options? The first one says if D divides n, then there exists a subgroup G of order D. So for every divisor, you have a subgroup of order D, and that's what we have already seen is true by converse of Lagrange theorem for abelian groups. So this is known to us that it is true. Next, if you have this subgroup replaced by element, then also does it hold true? I'm waiting for you to answer this question. I'll not give answer right now. Next one is if every proper subgroup is cyclic, right? You have a group, every proper subgroup is cyclic, then G has to be cyclic. Of course, for a cyclic group, you know that all subgroups have to be cyclic, right? I'm asking conversely, if every proper subgroup is cyclic, then is the group G also cyclic? So again, I'm waiting for you to answer if B is true or not, C is true or not. And then if you have a subgroup H, you're working in abelian case, does there always exist a group N, right? Going modulo which you get H. So H can be written as a factor subgroup is the question that we are putting in this. So let me see if I can have some answer. I'll wait for say 10 seconds because there is some time lag I can see. Now it is there on the screen. Okay, so somebody is saying B is not true. Take K4. And then there is another answer. Q8 is counter example, right? But Q8 you cannot take because we are talking in abelian groups, right? So the question says for finite abelian group. Again, for B, Z2 cross Z2, which is same as Klein 4 or K4 group. This is by S. Jan. And this is also correct. And Dimple is giving example of S3, but that's not true because we are talking of finite abelian groups, as I said. Okay, so the answer to B, in fact, does not need a counter example, though what you have said is correct. But in fact, that works for B and C both, right? In case of Klein's 4 group. So let me just tell for the students who are not aware, Klein's 4 group is name given to C2 cross C2, right? The smallest abelian group, which is not cyclic. And so here you have divisors as 1, 2, and 4, but there is no element of order 4. So this is a counter example, and also every proper subgroup is cyclic, but G is not cyclic. Right? But then you just can answer it by your understanding for the case B, that if suppose for every divisor there was an element of order D, right? G has order N is a divisor of itself, and if you have an element of order N, it will be a cyclic group of order N. So that simply means that every abelian group has to be cyclic, which is of course not true. So this was just a conceptual fact. So this is false, this is false. And I leave it on to you to check that D is also true, right? Because you're working in abelian groups. So there are some hints that I'm leaving for you to see this thing. You're working in abelian groups, firstly. Secondly, if D is a divisor, so you have this subgroup H, and if D is the order of that group H, then N by D is also divisor of N, and you do have a subgroup of that order in G because this is abelian group, right? So just put up these pieces of puzzles that I have put for you to get this answer that this is a correct option, and that fetches you 4.75 marks for this question, right? Generally for single answer, the questions are for 3 marks, and for multiple, they are 4.575. That's slightly higher. I do not remember exactly, but probably it is this way. Okay, so with that, I'll move on to the next slide where I have this question for you. Again, a finite abelian group. I'm not taking any difficult group for you. In fact, as I said, these are the questions from NET exam. This was asked in December 2017. Again, multiple choice, a finite abelian group. So if you have 2 elements of different orders, M and N, what can you say about order of AB? What can you say about order of product of these elements? So I'll again wait for say 10 seconds for getting the answer. What are your options? This is multiple correct options, okay? Yeah, the question is on screen. Right, I get this answer from Shraban Das, and that's absolutely correct answer, where you just pick B to be A inverse. Okay, so you have groups of elements of order M and M each, right? A and A inverse do have same order, but if you look at product, that is simply identity, which is order 1. So this is false, and of course this is also false. So you're just left with one option, which is C, and you have this answer. But suppose if if another option was there, E, none of these, how would you make sure that there is an element in G whose order is LCM of M, N? That you should be aware of, okay? This is something nice that you should understand. What is the element? Leaving you with a small hint here. Look for this element. This is not product of A and B, okay? This is not product of A and B. So this is somewhat like a copy of this CM cross CN that you are getting. This is isomorphic to this, and this is sitting inside your group G, if A and B are sitting inside G. Okay, and this subgroup is going to have, this element is going to have this order LCM of M and N. Just go about the details, just check out the details of this. Okay, with that, we have few more minutes left, and I would like to use them for some next questions. Okay, so now I ask you, what is the number of non-singular 3 cross 3 matrices over F2? By F2, I mean field of order 2, finite field with 2 elements. Okay, so non-singular matrices, you understand this. The question could also be, what is the size of general linear group on F2, right? This is just analogous, just a restatement of this question. What is the size of this? So see, such questions are also asked and can fetch you good marks, and that too very quickly, right? So if you have to look for 3 cross 3 matrices, that means you have to look for the entries of this sort, right? But then you have to make sure that the matrix is non-singular. So if you look at the first, yes, Saksham has got this answer correct, but let me explain it for others. So you have possibilities. You can fill any two elements here, any two here, any two here. But then the problem is you cannot have all zeros in the first row. So there is only one vector that you have to avoid. And this leaves you with 2 to the 3 minus 1 options for the first row. Okay. For the second row, what you need to take care is that this vector should not be dependent, it should not be linear multiple of the first one. So now if your vector is alpha, you cannot have lambda times alpha here. You cannot have any multiple of this vector, and your lambda, your scalar, is coming from field of order 2, right? So you have to get rid of how many choices you have to get rid of. You have all those 2 to the power 3, but you have to miss out those 2 which are multiples of the previous one, right? So that's why you have these many options here. And the other case you have that you don't have to take a multiple of any of these two. You don't have to take a linear combination of these two vectors above. So you cannot have, say, something lambda 1 alpha plus lambda 2 beta, where your alpha is the first row and beta is the second row. Having fixed that, you cannot take these choices, right? So how many choices you have? 2, 3 minus 1, 2 cube minus 2. Why I have written in this form, it will be clear to you with the next question that I put up for this general thing. Okay. Okay. So somebody is saying that this is a general question that they ask you for. This is the reason I have taken this question. This is really an important question, a basic but important question. And I'll just now give you a complete answer as well. So, okay. So this is the answer that you get. You can solve it to see the answer turns out to be 168. But as rightly asked, what is the answer to this question? Okay, this is in one of the comments. So let's just take up with this example, and I hope that will answer your question. If not, I'll go over details once again. So this is for you, Chinmay. Okay, P is a prime number, and now I'm asking, I've added something more to it. Silo P subgroup of GL50 FP. So this is, let's first look at this group. Okay, the cardinality of this group, and we'll talk about Silo P group later. So now what you have to do is you have to make a 50 cross 50 matrix, and the entries are from finite field of order P. So the first row, you have how many choices? You have P to the 50 choices minus 1. As you cannot have that zero vector, as I explained in the previous one also, right? So just use your counting principles. You have P choices for each coordinate, that makes it P to the 50 minus 1 for the zero vector. Now, if you look at the second vector, this was your vector 1, or row 1, I should call it. Vector 2, if you look at, this can be anything. So it can be P to the 50, but then you cannot take any multiple of the first row. And how many multiples you can have? As many coefficients you have, and that the choice is FP. So that will be P minus P here. Okay, that takes care of zero vector also, because zero is also a scalar in FP. So if you take all multiples, that 0 times this is also taken care of. Okay. And for the next one, you don't have to take linear combination of the previous two, and so on. And when you come at the last row, the 50th row, what will happen? You cannot take any linear combination of the previous 49. So that will lose you out with these many options, and you are left with these options. So the product of these is the cardinality of GL50 FP. Had it been N, so what would have been your answer? It would have been P to the N minus 1. There's nothing particular about 50, right? So I think that answers your question. And now the next part of this question is about Silo P subgroups, right? Silo P means you have to look for highest power of P, which divides your group. right? This is, I'm using this sign for highest power. That is, suppose if I have p to the 40 as highest power, that means p to the 41 will not divide G. And that is the size of silo P subgroup you're going to have. So basically, you just have to look for the highest power of P, which will divide the order of this group. Now, how many P's you get from here? None. From here, you get 1P. Then from next, you get P square and so on up to P to the 49. So now you have your answer 1 plus 2 plus so on up to 49. And this, you know, is 49 times 50 by 2. So this is, you have this as your answer. Okay. Once I know it is 49 times 25, I see it is not ending with 0. It is not ending with 0. These are the quick observations you should have to save time. And of course, it cannot be 125. That's 25 times 5. So that gives you your answer D, right? Okay. And so with that, I'd like to stop here because it's time. And in a nutshell, what I just wanted to take up with this topic is whenever you study a topic, read it in detail, use a lot of examples, a lot of counter examples, try to understand what are the properties that we have for that case and what are the properties that we do not have, right? What are the exceptions, possible results which can be true, which can fail, and just make best of the questions. That will give you good grip over the answers, right? Putting up right questions is what is the key to understand some concept. This is what I would like to say. And regarding exceptions, this is one thing I would like to say. They are paper setters' favorite choices, and they are more familiar than you with the exceptions. So you just can't get rid of those if you want to score high. You also be familiar with the exceptions if you want to score high, right? So with that, I'd like to stop. Over to you, Vivek.
Yeah. Thank you very much, Sugandha. And I could see that you have taken all the questions from the YouTube. So I don't have to copy it here. Okay, so we'll take a break of 5 minutes and then we'll come back for the next session.
Okay. Thank you, Vivek. I tried taking almost every question, but I'll just see if something is missed. Maybe I'll take just before the session starts. I'll not spend more than 5 minutes for that.
Sure,
okay?
Sure. Okay.
So join you at 10:40.
Yeah. So now it is 10:32. We'll start at 10:37.
All right.
Yeah, we can start now. So welcome back to session number 6 of this exam 21 workshop, and we'll start with the next session. Over to you, Sugandha.
Thank you, Vivek. I'll just share my screen. Just give me 2 more seconds. Are you able to see the screen?
Yes.
Okay, then we are good to go. Okay, so this is session 2 for today, and again, another very important part of abstract algebra, ring theory and field theory. And by schedule, I think you know that we are going to talk of irreducibility criteria, right? A very basic and very fundamental concept that we are going to take up. But yet, this is important, and there are a lot of questions which can be built around these. So, and unlike last session where I first told you about some concepts and then took you to the questions, here what I would like to do is I'd like to take up questions and tell you concepts alone, right? So I'll just brief about the definition and then we will move on to questions, okay? So what is irreducibility? I think you know it, but in general, like if you have to remember what is irreducibility, so in literal meaning, it is something which says which cannot be reduced, which cannot be broken further, right? In layman's language. And in mathematics also, this is very general term which is used for various algebraic structures also. So basically by irreducibility, we have that something which cannot be made smaller, any algebraic structure which cannot be decomposed into smaller one. Now this smaller could be depending upon the things which are important to us. For example, in case of polynomials, we have degree, which we look as, you'll just see what is the meaning of irreducible polynomial, right? So roughly speaking, when it comes to polynomials, we have something which cannot be factored, something which cannot be written as a product of polynomials of smaller degree, right? And if you talk of the factors or polynomials, then the important role is played by the coefficients which you are talking of, the coefficients from which ring they are coming, from which field they are coming, that is important. For example, a very simple basic example, if I pick of this polynomial, one can say that this is irreducible over Q, irreducible over rationals, because you cannot find a rational, factors to it. You can decompose this as x minus root 2 and x plus root 2. So, and these coefficients are over real numbers. So of course, this polynomial is reducible over real numbers, right? Similarly, if you talk of x, very simple examples I'm picking just to recall what is the definition. So x square plus 1, this is irreducible over reals, but then you can always write this as x plus I and x minus I. This is decomposable over complex numbers, right? You are working on the ring from which the coefficients are coming from, they play a vital role in deciding whether a polynomial is irreducible or not, right? Answerable only when you talk about the field of coefficients. Okay, so I'm giving you a definition. In fact, I didn't want to take up a definition because this is not in most general form, but we need something to begin with. Constant polynomial is irreducible over f if its coefficients belong to f and it cannot be factored.
Your slides are not visible.
Right, there was some glitch. I lost internet for a few seconds.
Okay.
I'll share again, and by that time, can you tell me what was the last thing that you saw?
Okay.
I think it was this slide that.
Yes.
Yeah. Okay, so as I told already, what is irreducibility? If you have a field f and you have a non-constant polynomial over that, then we say that it is irreducible if it cannot be factored into non-constant polynomials of smaller degree, right? This is how we define what are irreducible polynomials. But then there are some more general criteria to this. So you see the next definition. Now I'm saying your integral coefficients, right? Integers do not form a field, you know that. And in fact, you can talk of any unique factorization domain. I'll come to that as well. So this is said to be irreducible if it is an irreducible element of the polynomial ring. Okay, so that means it is not zero, it is not invertible, and it cannot be factored as product of two other non-invertible polynomials with coefficients from that ring. Okay, so you see here that I introduced this term of unique factorization domain, right? I introduced this new term. You have had a, I mean, I think you must be familiar with this, but if not,
Sugandha, we could not hear you. Oh, some network problem. Please wait for a few seconds. Yeah, you are back now.
I'm so sorry. I don't know what is the problem with. It's a very unusual thing, but yeah. So I'll show the screen again. Okay, so I was just listing out some questions when I lost the connection. So you need to understand. Wait. Okay. So you need to understand what are UFDs. As usual, I always suggest to write down some examples of domains, integral domains, which are unique factorization domains, and the ones which are not. And in fact, you will see the later ones are difficult to construct. They are not natural. And then you need to understand what are the properties that are enjoyed by these unique factorization domains. What are the properties that they have? So I'll talk of some standard examples of unique factorization domains and the ones which I'm going to use more or less very frequently today. So important examples of UFDs, they cover up integers, right? Then you have polynomial rings. And these could be in one or more variables. But we will more or less be concentrating on one with coefficients from Z or F, right? So this could be Fx, this could be Zx. These are unique factorization domains, and these are the ones which I will be using most frequently, right? Let me tell you before moving further that factorization of given any polynomial, factorization may not always be computed. This is not a very There is no one fixed recipe that we have for this, for given any arbitrary polynomial, and even the irreducibility of polynomial, that may not always be proved by computation, right? There are algorithms, there are ways, but there is no one way which works for all of them. And this is still a question which has no answer in general. But over integers, over rational numbers, or I should say over some particular fields, over some finite fields, we have some criteria, right, which with which we can check whether given polynomial is irreducible or not. So I will be talking about those cases where we do have the grip. Okay. Right. So I begin with this very simple question. In fact, this has nothing to do with irreducibility as such directly, but indirectly there is a purpose why I have kept this question. So this was question asked in June 2012, and it has multiple correct options to this. You are given two polynomials, f of x and g of x, and you need to find out GCD of these two polynomials and LCM of these two polynomials. This must not be a difficult thing. Like for example, if you have f of x, you can clearly see, you can factorize it, right? So this is just a high school algebra that you have to apply here. And gx, you know, can be factored as x plus 1 times x square minus x plus 1. So now you know what is GCD, what is LCM. GCD you can clearly see is x plus 1. So this is correct answer. And once this is correct, this has to be, because it is the GCD, right? GCD is always unique. And for the LCM, you have two choices. Of course, only one of them can be correct. And with this, you see you have this, for LCM, what do you have? X plus 1 times x square plus 1 times x square minus x plus 1. Have I written it correctly? Yeah. So now you can compute what it turns out to be. This has to be of degree 5. And by computing, you can find out the answer turns out to be this, right? But my point of taking it up here is that I don't have to evaluate this polynomial to make sure what is the LCM. This is what I want to highlight here. Why? Because, okay, no. I'm sorry, I tried to make some point, but that's not working. I'm sorry. I'm really sorry. The answer will be C. Yes, the answer will be C, and this cannot be LCM. This is what I'm trying to say. Okay, so at first I should be able to just get rid of this, and then the remaining option is your answer. How do I eliminate this option? One thing that you know for sure is LCM here is multiple of two distinct polynomials, right? You have the first one also as factor of it, second one also. So LCM is not irreducible for sure, but the polynomial that you see here, this is an irreducible polynomial, and we will come to this in a while. So let's not waste much time on this. This was just a trivial question that flashed to me, and I thought I should take it up. Okay, so there is this another question where you have two polynomials and you have to decide the irreducibility of these polynomials. This is single correct choice question. So once you have the answer, one answer, you don't have to take care of other options. Okay, so how do you check irreducibility? As I said, I'll be telling you the ways, the criteria along with the question. So you see these are polynomials of degree 2 and 3, and you have to check the irreducibility over Z3, right? Look at f of x and g of x also. Suppose any of these was reducible. Suppose any of these was reducible, then the degree of the smaller, the factors would have been strictly less. So there has to be a 1 degree polynomial, right? There has to be a linear factor attached to them. So it could factor as all 3 linear factors or a degree 2 and degree 1. And here it has to be both degree 1. So you cannot get rid of a factor of this form. X minus alpha has to be a factor if your polynomial is of degree at most 3. And that means if x minus alpha is a factor, that means x is equal to alpha has to be a root of that polynomial. Okay. So now if you look at f of x and you have to check over z3. Okay. So now if your scalars are simply 0, 1, and 2, and you just need to check if any of them is a root of the given polynomial. So you can very well check f of 0 is simply 1. F of 1 is 1. F of 2, if I look at, this is 2 cube plus 2 times 2 square plus 1. So this is 8 plus 8. So this is not, this is reducible. Okay. And how about this one? If you, so what I'm doing is I'm just checking for the possible roots that I can have, and I'm working this modulo 3. Okay. And this will be 8 plus 8. So this is minus 1 plus 1 minus 1, or 2 modulo 3, because we are working in a field of characters, in a ring of characteristic 3. Okay. All right. And how about gx? You can check by the same way by putting 0, 1, and 2 if any of these satisfy. So if I put 0, I get 2. If I put 1, I get 5. And if I put 2, then I get 8 plus 2. Yeah, then it is 0. So the x minus 2 is a factor of g of x. So this is not irreducible. This is reducible. So that gives you your answer as option B. Okay. So this is simply root test, what we call as, but this is, be careful that this works only for the case of degree 3 and not higher. So here is the next question that you see on your screen, which asks you which this polynomial is given to you, and you're asked whether it is irreducible in any of the fields. So the fields are varying here, and you have to check for the irreducibility of this polynomial. So again, because this is degree at most 3, so that works for you, right? Because this is of degree 3, it must have a linear factor to be reducible. So there should be a root of this polynomial. Okay, then what you can do is you can simply keep substituting the values to see. That's one way how you can check this thing. Now, if I put x equals 0, you'll be left with just the constant term, right? And there is something special. You can just verify with that if you put x equals 0, this will be 0 modulo 3, right? So let me call this polynomial as f of x. You will be able to see that f of 0 is simply going to be 0 modulo 3, because both these terms, they are multiples of 3 that you can check by simple divisibility test by 3. That's okay. Okay. And if you, this will also be congruent to 0 mod 7. So this you can check that this number is divisible by 7 and also by 13. So you will get mod 7 here. So that means this is reducible over each of these fields for sure, right? But over Q, how would you say that? Suppose again, if there was an option E, how would you make sure that it is irreducible over Q? From this, you have that this is the only correct answer that you can have. Method of elimination gives you that. So here are two things that I would like to talk about. Let's first talk about these numbers that appear. You see these numbers are of the form ABC, ABC, right? There is this structure to these numbers that you have. So what is so special about these numbers? Just write this in expanded form as you used to do as a kid, right? So this is some number theoretic flavor that I'm giving to this problem. Right, so this is the number and this is its expansion. And now if you just pair up these, you have 10 cube plus 1, and similarly you have 10b 10 cube plus 1, and also with C you have 10 cube plus 1, right? So 10 cube plus 1 is something which is common to all of them. This leaves you with something which I'm least concerned, and this is 1001. And if you write down the prime factorization of this, you of course know that this is divisible by wait. Yeah, so you see this 1001, this is definitely divisible by 11 because sum of odds and evens you can just apply. And then you have this 99, and this is divisible by 13 and 7. So the prime factorization of this goes like 7 times 11 times 13. And that tells you each of these numbers is divisible by 7, 11, and 13 for sure. For 3, you can just orally check for this case because 1 to 3 is 6. So this is divisible by 3 for sure, right? So had there been F11, then also it would have been reducible over that, right? That's something you can observe for such kind of numbers always. It's divisible by 7, 11, as well as 13. Okay, that is one thing about the numbers. Second thing, I want to talk about this Q. Why should this be irreducible over Q, right? If you have to make sure that it is irreducible over Q. So for that, I will introduce you Eisenstein's criterion. Again, a standard basic thing, and maybe most of you know about it. So what is Eisenstein's criterion?
It's 11 o'clock.
It says if you have a polynomial, right, of this form with the coefficients from integers, and if there is a prime number p, if there is any prime p that you can find which divides each of these coefficients except this one, except the leading coefficient, right? So if it doesn't divide the coefficient of the highest power and divides the rest of them, that is one thing. Second thing is that it does not divide, the square of it does not divide the constant term, okay? P square should not divide A naught, right? In that case, your polynomial is going to be irreducible over rationals, right? Is that clear to you? So what do we have? We need to make sure that a polynomial is irreducible using this criterion. You need to have a prime p which divides all the coefficients except the leading one, and the square of it does not divide the constant one, and in that case it becomes irreducible over rational numbers. So if you look carefully at this polynomial which I listed, you can work with any of these primes to make sure that this is divisible. For example, if I have prime p as 3 only, the last coefficient that you see, p square, does not divide it. The sum is 12. The sum of digits is 12 and it's not divisible by 9. So with Eisenstein criterion, you have that this polynomial is indeed irreducible over Q. Okay, so we have for degree up to at most 3 that this linear factor should be there. There should be a root, and we can check over finite fields very easily. For Q, we will just see. And for also we have a reducibility using Eisenstein criterion, right? So here I leave you with another question, and I expect you to give some answers. So let me see if some of you can give me answer. You have this polynomial of degree 3. Is it going fine, Vivek? I'm just concerned because on YouTube I do not see this moving.
Sorry?
Is it going smooth? Because on YouTube I see that there are some disconnections.
No, it is working fine.
Okay, sorry for the interruption then. Okay, so look at this question. You have polynomials and you need to check the irreducibility over the given rings. Okay, the first one is over Q. And what is the first thing that comes to your mind? The Eisenstein's criterion that you have just seen, and you can work this with prime p equals 3. Okay, and for the second one, again you have this degree 3 or less, so you can check for B. That shouldn't be a problem, right? I'm not marking this as answer. I'm just saying that you can judge for this whether this is irreducible or not, right? And so you need to answer for C and D. For C, again, you can see very easily the factors can be written, right? X plus 1 plus 1. So because you have a factor, this is not irreducible. This is definitely reducible. This is irreducible for sure. For B, I leave on to you to check, and you will be able to check that this is again reducible. You will be able to find a root here. Now the question is, sorry, the question is about D. So this is a polynomial that I'm talking about, and I claim that this is an irreducible polynomial. Why is that so? That is something that we will have to look at. Okay, so and the hint to this is, the answer to this comes again by Eisenstein criteria. How? Let's see. So unlike last session, I'm not able to take questions from the chat box right now because there is some interruption that I see. I'll take them at the end. Feel free to write your questions in the comment box. Okay. So this irreducibility of cyclotomic polynomials, if we talk of, so what are cyclotomic polynomials? You must have heard this term at least. What are cyclotomic polynomials? So I look at this one, which is x to the p minus 1 over x minus 1, and this factors like this, right? So this is equal to x minus 1 times this. And my claim is that this is an irreducible polynomial. This is not for general n, but this is for prime power that you have, that this will be irreducible. Why is that so? That follows very well from the Eisenstein criterion, because if you look at, if you just make this substitution, x going to x plus 1, right? So on the left-hand side, you're going to get x plus 1 to the p minus 1 over x. And by applying your binomial theorem, you have this expansion. Now, by simple number theory, you know that p divides each of these coefficients, right? And the last coefficient is simply p. So p squared does not divide the constant term. It does not divide the leading term. The square of it does not divide the constant term. And p divides each of the remaining coefficient. So by Eisenstein's criterion, you have that this polynomial is irreducible. And of course, fx is irreducible if and only if f of x plus 1 is irreducible. The substitution does not change its nature of irreducibility, right? So with this, we have this thing to remember, that a polynomial of this type is always irreducible. So remember in the that case of this LCM question, I said that I know it beforehand that this is irreducible. So this cannot be LCM. You can strictly cancel this option. This is because it's a cyclotomic polynomial, okay, of this form. So x to the, so I'll just highlight that once again. This is something that you should remember, that x to the p minus 1 plus x square so on up to x to the p minus 1. This is always irreducible over z. Okay, so that brings me to the next question for you. It says that if you have f of x as this 3-degree polynomial, you have to determine the irreducibility over the fields which are listed for you, right? So this was also in multiple choice questions asked in June 2013. And so what are the answers that you can give at this stage? degree 3. So you can very well handle these two cases, right? You check for 0, you check 0 and 1. In the first case, 0, 1 and 2 for the case D. And so what is your answer? Can you tell me? But as I said earlier, I can't be waiting for answers. This C will be irreducible, but here you do have a root over F3. Okay, if you put x equals 2, I think it must satisfy all. Just check it out. Just check it out for yourself. 0 does not work. 1 works. 1 works. Okay, so f of 1, if you look at, that is 1 plus 2 plus 1 minus 1, and this is 0 modulo 3. So you have that this x minus 1 is a factor of this. So these two options you have handled. Now among A and B, you have to answer. Let me first talk about B over reals. Okay. So suppose if the field was complex numbers, you would be able to write this as a product of linear factors, right? C is algebraically closed field and you have all the roots in that field. And for the reals, if you have to look over reals, you know the complex roots occur in pairs, right? So because this polynomial does not have any complex coefficient, you are definitely going to have a linear factor over reals, right? So x minus alpha, and then whatever roots you have in pair with that, you will have a quadratic or maybe linear if those factors are over real. So at least you have one linear factor, right? And this is the reason that over R, this has to be reducible. In fact, any odd degree polynomial over Rx, this is field of reals, is reducible. Okay? X minus alpha will always be a factor of this. So you have set an answer for this. This is reducible. This is not irreducible. And coming on to the field of rationals, this is something important. So over finite fields, you chose all the scalars and you just tested to see if it works or not. But over rationals, what do? It's an infinite field. You can't be going over all the values. You don't have to, in fact, because if you have x minus alpha, alpha is a linear factor, alpha is a root of this, then it must divide the constant term. So the reason for that is very simple. So suppose x minus alpha is a factor of f of x, right? This means that f of alpha equals 0. That's a root of this polynomial. And that will mean that it divides. So I'll just use this 1 equals 0. And now if you look at, if you just shift this constant term to the other side, what do you have? That alpha divides each of these. So alpha must divide the constant term also. Right? So you just look for the divisors of 1, which are plus and minus 1, and then you can substitute to see whether f of 1 is 0, whether f of minus 1 is 0. So this is 1 plus 2 plus 1 minus 1, which is clearly not 0. F of minus 1 is minus 1 plus 2 minus 1 minus 1, which is again not 0. So that means it is irreducible over Q. Okay, so your answer is A and C. All right, with that, I move on to next question now. Enough of degree 3. We have some information about degree 3. Simply root test gives you your answer then. But if you have a degree 4 polynomial like this, then what do you do? So for this particular question, this is again multiple correct options you have. It was asked in June 2014. So for this particular question, there is a notation introduced here that you see fpx. So you have this polynomial, and for a prime p, they say fpx is polynomial. I'm sorry, something is probably missing here. Denotes the polynomial with coefficients over that field. Okay, coefficients in z mod pz it should be. So basically what you have to do is you have to reduce the coefficients modulo p. If this notation was not given, we were already doing it. right? So there is nothing new, but you have to be careful about how the things are defined. Look at option A. Here they're asking you if f2x is irreducible over z2z. And this is the same thing as what we have been already doing, that you need to check whether the polynomial is irreducible over z2 or not. But then now the problem is it is degree 4. You cannot apply that root test just by verifying if 0 or 1 is a root of this or not. You cannot say whether the polynomial is irreducible or not, right? Because this being degree 4, you can have 2 quadratic factors, right? You can have 2 degree 2 factors each. So that could be a decomposition of this. This could still be reducible even if you don't have a linear factor attached to it. So suppose this was the case, then it would have been somewhat of the form x squared plus ax plus b, x squared plus say cx plus d. Why I'm taking the coefficient of x square equals 1? Because this is a monic polynomial and we are just concentrating on z for the time being, z or z mod 2z and so on, like this for the time being. So if you look at this, right, then let's start with this z mod 2z itself, okay? So this should be same as what we are saying is, I'll write it neatly here, x squared plus ax plus b, x squared plus cx plus d. This should be equal to, we want to see whether there is a decomposition of this one. Firstly, you check whether there is a decomposition for a linear one. That means you check for f of 0. So f of 0 you see is everything here will be 0 and this will be 1. F of 1, if you see, will be equal to 1 plus 1 plus 1 plus 1 plus 1, which is of course 1 modulo 2. So it has no linear factors over z2, that is for sure. If it has, at most it will have quadratic factors. So that is why I have chosen these to be factors. And now what I'll do is I'll just erase this extra part so that you are able to see what is important. So why isn't this working? Okay. Right. So now what you do is, this is over 2. So I can just reduce this. This will be x4 plus x cube plus x square plus x plus 1 that you have. And now if you start comparing the coefficients, you will realize that you cannot find any suitable choice of A, B, C, and D. I can do it right away, but that's nothing constructive. That is nothing conceptual. So you just can compare the coefficients to see that you don't have any answer to this thing. So this will be irreducible over Z mod 2Z, right? Similarly, for Z mod 3Z, we can check. But for Z mod 3Z, you don't have to do much. You see, firstly, you see that f of 0, what is it? These all will simply disappear, being multiple of 3. So you have your f of x in this case becomes x to the 4 plus, plus x only, right? And f of 0 is a root. Right? The constant term is divisible by 3. So this has a linear factor. So this is not irreducible over Z mod 3Z. That is for sure. Now the question is about irreducibility over Q and irreducibility over Z. Something very important that I would like to point out here. In fact, Eisenstein's criterion is also not applicable because you see the prime 3 divides everything, but square of it also divides constant term, and also there's 7. So that's not applicable at all. And of course, not the cyclotomic polynomial. This is not a cyclotomic polynomial. So here I would like to point out something, that irreducibility over Q implies irreducibility over Z, right? So if something is irreducible over rationals, then it is also irreducible over integers. That's not very difficult to see, because if suppose if this was reducible over z, I'll just prove the contrapositive of this. So if this was possible to write this as product of two linear factors in z, right? They're of course polynomials over q. So that will make it reducible over q also. So that's not something very difficult. So suppose if we are able to prove that b is true, then d will automatically follow. And if not, then we will have to check for d. In fact, here I would like to point out, if the converse of this, it's not true in general, but if you have that your polynomial belongs to this and is also monic, okay? So here I'm just being a little more careful about irreducibility, the meaning, the definition that we're using for irreducibility, because irreducibility or being a prime, and so all those concepts, there are some more things associated to it. So I'm making it more precise by saying if f is monic, then the two concepts are equivalent. Converse is true. So checking over converse is true. So checking over z or checking over q will be same. This you can, so what I'm saying is the coefficients are integral. So again, this you can just simply write down the reducible factors, and then by clearing the denominator, you'll be able to see how this monic things plays role, and this is not difficult to prove by yourself. So irreducibility criteria here are equivalent for z and q. So let's concentrate on this thing to see whether it is irreducible over q or not, right? So at present, we know A is true, C is false, B and D, either they are both false or they are both true, depending upon something called as mod P test. So this is another criterion to check the irreducibility of polynomial over Z. What does it say? It says that if you have a prime P and your polynomial is over Zx, if fpx, remember the notation I give you, that if you reduce all those over, reduce the coefficients modulo P, and that polynomial is irreducible in Zpx, right? Also the degree is not reduced, also the degree remains the same, then fx is irreducible over Z. Remember, this is very strong test in the sense because you have to do this for any prime P. You just have to find a prime P which satisfies this thing. Okay. So if you have a polynomial, you go modulo P for the coefficients, and if it remains irreducible there and the degree is not lessened, then it has to be irreducible over Zx. So let's just apply it to the previous question, and then I'll talk a little more about mod P test as well. So if you look at this, what is the prime that we should take up? Not 3 at least, because over 3 you have seen it is reducible already. Maybe I'll begin with 2 itself. Okay, so over 2, oh, of course you have already checked it over 2. That f2x is irreducible over this thing. So mod P test tells you that it has to be irreducible over q also. So you have these 3 as correct options. Okay, so you need to find a suitable prime P which satisfies these criterion, these things to say whether the polynomial is irreducible or not. Okay. Something that you need to be careful about. How about the converse? Like suppose if I'll just go with an example for this. Suppose if I give you this x4 minus 10x squared plus 5, this is a polynomial that you have. And you look at, you check this with p equals 2. Okay, this is irreducible over Z. Is it true or not? This is irreducible over Z. And what is the reason? I've constructed in such a way that Eisenstein's criterion is true here. 5 divides 10, 5 divides 5, and 5 squared does not divide the constant term. So it is irreducible polynomial. But if you look at f2x, Look at f2x, that will be x4, this is 1, this is +1 or -1, and this factors as this in z2 over z2. So this is reducible there, right? So mod p test is not giving you any answer for this, but this, be careful, be careful. This is not converse of mod p test. So my question is not valid if I ask you whether converse of mod p test fails via this example. What will be the converse of mod p test? What will be the converse of this statement? Here we have, if there exists a prime p which satisfies these conditions, right? So the converse will be for every prime p, right? So my question to you is, if for every prime p, such a thing is not satisfied, then can you still say that fx is reducible over z? So my question, my homework for you is, firstly, to write converse of mod p test carefully. Okay. Second, to know, is it true? I shouldn't be giving you all answers that will stop you from thinking. Okay. So now the next part of my talk will be around why are we studying so much about irreducibility criterion. One thing is clear, that there are direct questions when they ask you whether some polynomial is irreducible or not, and you have seen it's not only the single correct options questions which are there, but also the multiple correct choice questions are also asked based upon this thing. But then there is this different set of questions that you can be asked around this very concept itself. Okay, so I'm looking for this application of irreducibility in field theory. If you have had a course in ring theory, you must be familiar with what are integral domains. So you know what is a ring, you know what is an integral domain. If not, of course, you need to. You cannot get away with these. Also, I've told you about UFDPIDs. I'll talk about them a little more. But the basic ones are prime ideals, maximal ideals. So these are the concepts done in very first course. So I assume that you people know it, and if not, please be familiar with them with lots of examples and counter examples, of course. And you must have seen this result. I'm quoting two results here. The first one says that if R is a ring and I is an ideal of ring R, then this quotient R mod I is a field if and only if I is maximal ideal of R. And there is also the statement about integral domain, R mod I is integral if and only if I is prime ideal, right? You should once look at the proof of this very carefully. You should know why does this happen. But here we are going to just look at application of this. So this is for any ring R that you have. If you know something about ideal I, whether it's prime or maximal, then you know about its quotient, whether it's integral domain or field. And there is this next result that I have written here, that if R is a PID, PID stands for principal ideal domain, okay? So if you have this R as PID, then this ideal generated by this polynomial f of x, this is maximal ideal in R if and only if f of x is irreducible. Okay, and if it is reducible, it decomposes and you have this Chinese remainder theorem coming into picture, what sort of rings become. So maybe this a question for you, if f of x is reducible, suppose it has factors, then look at structure of R mod f of x. What will this be isomorphic to? Okay. Of course, it won't be a field, because if it is reducible, it is not maximal ideal, but it is ideal. So R mod I makes sense. And that's not a field, but that is a ring. What is it isomorphic to? So you should look into this. This is an exercise for you. Okay, coming back to what we were doing, you have a PID generated by polynomial, you have a PID in that, you have an ideal generated by a polynomial, that will be maximal if and only if your polynomial is irreducible. Okay. In particular, because F, if you take as field, you have all the good properties there, that happens to be PID. And if you take a polynomial over f of x, then this ideal is maximal if and only if f of x is irreducible. So what do you get if you look at f of x modulo this polynomial which is over the same field? This will be field. In the nutshell, what do you get? If and only if f is irreducible. Does that make sense to you? Okay. So I have said certain things, assuming some things, but if the things are not clear, I'll just state some facts that you should be aware of, that you should be knowing. Okay, fx is nice for us. If f is field, then we even know that this is Euclidean domain. So I'm introducing a new term, Euclidean domain. So I've talked about Euclidean domain. And then you have this PID, right? You have this UFD, which I talked about in the very few first initial slides also. And so this is the direction, these are the implications that we have. If something is PID, it has to be UFD. If something is PID, it has to be UFD. But the converses are not true in general. A UFD need not be PID, a PID need not be ED, and please look into counter examples for sure. So I said earlier that the counter examples are favorites of paper setters. I would like to add to it, these are even important for your interviews. Okay, that's something I'm saying from a student's point of view back then. So be very much familiar with counter examples for sure, and they're generally not very obvious. Okay, so please look into the concepts of what is the meaning of ED, PID, UFD, and the implications that I have told you, why they are true. The converses are not true in general. So what are the counter examples that you have? And for example, this one I can tell you that ZX, right? Polynomials over integers. This is a UFD, but not a PID. Right? This is not a PID. Why is it not so? Just look into it. I've already told you to find out what are the good properties that you have once you have that your domain is UFD. And in fact, if you study this, you will come across the concept of prime polynomials, prime elements, right? And irreducible elements. I'm not saying polynomials right now because I'm talking about general domains. So prime, if you have integral domain, if you are working in an integral domain, then a prime element is always irreducible. But converse may not be true, right? But if you have R as PID, in that case, these two concepts are equivalent. So firstly, you need to understand how do we define prime elements, how do we define irreducible elements, and then you will be able to appreciate the difference between the two, right? But because we are working more or less in PID all the time, there these two concepts are equivalent. So your irreducible polynomials behave more or less like prime numbers in natural numbers that you have. Okay, right. And I've already told you that ZX is a UFD but not PID. About Z, you should know that this is PID. Okay, ZX is not a PID, but Z is. In fact, whenever you have unique factorization domain, its polynomial ring is also UFD. You can check this, right? But this is not true for PID because you have just seen that this is a PID, but this is not. right? And whenever you talk about f, that is UFD. And so f of x is also UFD. In fact, you have all the good properties here. So that's something you don't have to worry about. And z is a UFD. So zx is also UFD, right? So maybe this is a little confusing if you are not clear with the concepts, or if you're looking them after a long time. Just that in general, what I want to highlight is z, you should remember, z is a PID. Zx is not a PID, right? Fx is all good, is PID, is UFD, everything, all good there. Any other fact that I want to use from? Okay, right. So in the nutshell, if you go back to this slide, which I told you earlier, that R mod I, in a PID, you have this maximality condition coming from irreducible. So whenever you apply that this polynomial is irreducible, implies that this is maximal ideal. You just need to be sure of that the ring that you're working with is a PID. That's it. And ZX is not a PID, is something that you have to take care of. Okay, let's take up this question, which says that you have this ideal, you have this ideal generated by these two polynomials, and you have to check whether these quotients are fields or not. And clearly, because Q is a field, QX is PID, so you can apply your criteria. What you need to check is just whether these polynomials are irreducible or not, right? Another way of putting this question from ring theory or field theory, but the question is actually dependent on what we did earlier. So can you quickly check that the first polynomial is definitely not irreducible, because you can just use your high school algebra to see that this is having factors. So of course, this is not reducible. This is reducible. And how about this one? Again, very simple factorization. There's nothing that you need to do. So this tells you, because both of these are reducible, none of the quotients is field, and you have your answer here, right? So this fetches you 3 marks. And let me see what more questions we can. Okay, look at this question. Which of the following quotient rings are fields? Now I expected answer from you, but because I cannot have access to YouTube right now because of some technical issues. So let me just go over this discussion, and probably this is the last question that I have for you. And then I'll talk about a few more things. Okay, so you need to answer whether these are fields or not, right? So I'm not talking about A, I'm not talking about C, I'm not talking about D, because these are less than degree 3 polynomials, right? They are degree 2 polynomials, and you can very well check irreducibility now. In fact, for 3, I can directly see 1 plus 1 plus 1 is going to be 0 modulo 3. So this is reducible. This is not a field. And for this is reducible. For this also, I can see that this is going to be irreducible. So these two are indeed fields, right? Now for this, you cannot apply the same criterion to say whether x minus 3 is maximal or not. It is though irreducible, it is linear factor, it cannot be broken further. But you cannot say with that criteria whether this will be field or not. But remember, I told you that this R mod I is field if and only if I is maximal. This is applicable for any ring R, right? This is not restricted to PID or UFD. So if you look at this, just look at this ideal x minus 3. This can be embedded in another ideal. If I take some other constant here, this can be embedded in that, right? So this is not maximal. And because this is not maximal, this is not a field, right? So you have your answers as C and D. Right, let me see if I have any more questions. No, that's all for now. And with this, I would like to stop, leaving you with lots of homework, lots of theory to be seen, and in addition to the assignment. So I spent some 4 or 5 minutes talking about some things that I want to share from my experience. So first thing is disclaimer that I would like to put this up, that this is entirely my personal opinion about attempting question based on my experience as a student, and it may not be universally applicable to all of you, right? So be choosy in picking up the tips that I give you. So the very first thing is do preparation in full swing. There are no shortcuts, no workshop or no concise thing can actually give you a proper recipe to get through these exams. You have to do preparation in full swing. You have to understand each and everything very carefully, right? That's one thing. Then strategizing your preparation as well as attempting is very important. Be choosy in topics, maybe, right? You may not choose to attempt all questions or all sections, but within a topic, do not make choices. Whatever you do everything in totality, because as I said, the things where you will leave, okay, this is the part which is not very easy or not very nice, the questions are going to be from there because the teachers or the paper setters, they are more familiar with those things. So rather than making choices there, do everything. And if you want to make a selection, make selection topic wise, okay? Remember results, whatever results you study, but still work out the proofs. These proofs will give you a better retention. You will be able to remember the results, as well as the point is when you write down proof, there are so many concepts used, there are so many previous results being used that it will help you not only understanding, but because those cross results are used, they will help you retaining more, right? And the other thing that I always keep saying in general to learn mathematics, to understand mathematics, or maybe applicable for other subjects also, curiosity questions, very important. Put questions to yourself, whether this will be there, whether this will not be there. Make good questions, that makes good learning. Okay, and for attempting, strategizing is very important with respect to marks as well as time, because the questions which will take more time will fetch you more marks, but then you need to make some priority because there are some choices that you can make. In first attempt, you should be able to make out what are the questions that you will be able to solve. And this is the thing that I've also tried to put up in my assignment. You will see you have mixed questions. It's not that it goes easy to difficult or anything. So you need to kind of make out what are the questions that you will be able to do and the questions which you should do firstly. So do this assignment with a fixed time, say maybe half an hour. And after that half an hour is over, you can keep attempting the remaining questions also to see whether you can attempt or not. So just try to strategize, because you might spend a lot of time on some question, and that also is going to give you equal marks as the other one. And the last but most important, to get an edge over other competence, or I should say to be in top layer, to be in top cream, the questions which are going to fetch you those marks which take you to the top slot, those will be the questions which will be interrelated in various subjects, more or less. I mean, this is what I infer, this is what I think. You cannot really be just attempting for that kind of result. You really can't be attempting the questions which are just involving one concept. So in that case, you need to do things interrelated. Okay, you have to understand everything. And anyways, you will always need the concepts that you learn. You will need them for future, not just for clearing exam, because after that, either you're teaching or you're going into research, and you need all those concepts. And for entering purpose, as somebody was also pointing out regarding the interviews in the chat box. So in the interview, you can't be saying, okay, I guessed this question, or, I use this method of elimination. You need to be thorough with the concepts. So that's the bottom line, and that's all for now. Over to you, Vivek.
There are a couple of questions. I put it in the chat box.
Sorry, I couldn't hear you.
Questions which I was pasted in the chat box.
Okay. Thanks for writing the question. So, right, this is my question, which has been asked by some student. If R is a UFD, then RX is UFD. What about the converse? This is the question I forgot to write, but you will have to find it out for yourself. I can answer, but I will not right now. And in integral domain, is it necessary that R is commutative ring with unity? That follows from the definition of integral domain, right? So just get your definition of integral domain clear and you have answer for that right away. Can you please give some idea so that we can score maximum marks in section C of CSIR net exam, because that portion creates some problems for me to get good rank. I think I already answered this question because I expected this. How to claim that any infinite group cannot have exactly 3 subgroups? I'm not sure if this question is correct. How to claim that any infinite group, okay, cannot have exactly 3 subgroups. So I'd probably answer this separately. This is not something relevant to everybody because the scope that I picked up for this topic, it doesn't confine to that. And the next question is again on infinite groups. So I'll maybe, okay, so there's another thing being asked about references. Okay, thanks for asking that. I was to point it out, but I forgot somehow. So I'll give you some references, which, of course, any good book that you pick, that you understand concepts from, that will work for you. I'll write down some. So this is the first book that I studied as a student and that I refer to everybody is Contemporary Abstract Algebra by Joseph A. Gallion. Okay, this is such a good book. When you are reading group theory for the first time, you can read it all by yourself and it covers up almost all topics in very nice way. It has number of exercises and the exercises are given in such a nice way. Like I said, okay, this should be the next question. This should be the next question. So if you attempt those exercises, you will realize that it helps you in concept building. It's a very good book and this is a must suggested by me to all the students. It has concepts on group theory, ring theory, field theory, and also something about linear algebra. It talks somewhat about vector spaces also. So this is first book that everybody should be familiar with. When you're reading some concept for the first time, this will be good reference book for you. The other thing is Dummy and Foot. So this is Abstract Algebra by Dummy and Foot. This is the one that I'll refer for exercises, especially Galois theory is very well described there, which is very important topic in this area. And so this has a lot of questions, a lot of good questions, exercises, and it's very descriptive. But I mean, this is a good book, but then for basics, one should go for Gallion. And then for even better understanding, to be having even better grip over the concepts and also preparing for interviews or, so these are 3 books by, so for algebra, there are these books by Luther and Passy. So you have volume 1, 2, 3, and 4. So first is groups, the second is rings, then you have modules, and then you have field theory. And these are the books which let you understand these topics even more detailed. So you have some good grip, some understanding from Gallion, and then you can solve some more exercises from this. And so it's not that you have to, I mean, my way of guiding would be that you look at the syllabus, you just choose, you already have first courses in your colleges or universities. So pick up a topic and try to see what are the things associated to it. What do you know, what you need to know, and then look at the questions. And regarding questions, so there are these past year papers that you can find on the CSIR website itself, okay? And I wouldn't recommend any other source because these are authenticated, and there are a lot of solutions available in the market. I do not know, and I've never been through those, so I cannot say how reliable they are. That is up to you to check. For any exam, I think there is a lot of material appear in market. But why I'm talking about it is that my juniors, my colleagues recently compiled this set of solutions. So it's by Kanika and Gaurav Mittal. So they have had their PhDs, and they were my juniors since post-graduation at Punjab University. She's working at Isomorphism currently. So they have published with the Blue Rose publishers. Maybe you would like to have a look from this also. It's just that because they are my colleagues, so I'm aware that such a thing is available in market. And these are not very old. A couple of years back, she told me about this thing. So maybe you can, and something similar also you can. So yeah, these are the references I have.
Okay, so thank you.
Thank you very much for this excellent sessions from Sugandha. I hope students must have enjoyed these lectures, and this lecture will be available on YouTube channel, so you can again view it anytime. So that's all from today. We'll stop here for the today, and tomorrow again we'll meet at the same time, 9:30. You have to join at the YouTube channel, and the next session for the day 4 will start at the 9:30 tomorrow. So bye bye for now. Okay. So we can stop now.
Yeah. Right. Thank you, Vivek. Bye, everybody. Happy learning.
Okay. Madhu, you can stop streaming.